Hello students, this is Vijay Haushir. In the last lecture, we have studied about the bait isotherm, that is the Brownier, Emmett and Taylor isotherm of the surface chemistry chapter. So, in this lecture, we will study the classification of different adsorption isotherms. So, we have already studied the two types of isotherm, that is Freundlich adsorption isotherm and Langmuir adsorption isotherm. Due to some limitations of Freundlich and Langmuir, the BET, that is Brownier, Emmett and Taylor, also explain the adsorption of gases on the solids. So, these three types of adsorption are classified in the different adsorption isotherms. So, what are the classification? What is the classification of this type of adsorption isotherms? So, we will study the type first. So, what is the type first? That in the type first, the isotherms are typical of microporous solid where only monolayer adsorption occurs. So, we have already studied that in the Freundlich adsorption isotherm, what happens? There is formation of multilayer, but in the Langmuir adsorption isotherm, there is formation of monolayer. So, in the type first, the isotherms are typical of microporous solid where only monolayer adsorption occurs. So, if we plot a graph of adsorbed amount of substance divided versus the relative pressure. So, we got a graph like this. So, adsorbed amount versus relative pressure graph is plotted, that is called as a adsorption isotherm. So, in this micropore filling occurs significantly at relatively low pressure. Micropore filling means what? There is adsorption of some solids on the gases. So, how the adsorption of solids on the gases takes place? Because on the gases there are some micropores, and in this micropore filling occurs at relatively low pressure, means the solids adsorb on the gases at relatively low pressure, and that is given by less than 0.1 P upon P0, means less than 0.1, the relative pressure is less than 0.1 P upon P0, and the adsorption process being complete at 0.5 P upon P0, means the whole adsorption process, that is adsorption of solids on the gas, is completed at a relative pressure of about 0.5 P upon P0. And the example of the type first adsorption isotherm, that is here, is the formation of monolayer, and the graph is what is the adsorption isotherm? So, graph of adsorbed amount of gas versus relative pressure, that is called as adsorption isotherm. And the example is the adsorption of nitrogen gas on the microporous carbon, that is a charcoal. Microporous carbon is also called as activated carbon at 77 Kelvin, means this temperature is a constant. So, this is called as a isotherm. And second example is the adsorption of ammonia gas on the charcoal at 273 Kelvin. So, these are the two examples of type first adsorption isotherm which involves only monolayer adsorption isotherm. First example is the nitrogen on the carbon at 77 Kelvin, and second example is the ammonia on the charcoal at 273 Kelvin. So, this was about the type first adsorption isotherm. So, next is the type second. So, what happens in the type second? Type second isotherms describe the physical adsorption of gases by non-porous solids. Means in the type first, the adsorption was on the porous solid, and in the type second, the adsorption of gases by the non-porous solids, means the solids having non-porous structure, means no pore filling. So, what happens? The monolayer coverage is succeeded by multilayer adsorption at relatively higher pressure value, that is P upon P0 values. Means in the type first, the adsorption was up to monolayer and at relatively low pressure, that is less than 0.1 P upon P0. But in the type second, due to non-porous solid, what happens? The monolayer coverage is extended to the multilayer adsorption and relatively high pressure is required, that is relative pressure value is P upon P0 values. So if we plot a graph of adsorbed amount versus relative pressure, means in all types of adsorption or isotherm, we plot a graph of adsorbed amount versus relative pressure. So we obtain the graph like that. So this is the adsorption isotherm for the monolayer exceeded by multilayer adsorption. For type second, that is the adsorption of gases by non-porous solid. Next is the type third. So in the type third, what happens? The isotherms are obtained from carbons with mixed micro and mesoporosity. Means the isotherm which are obtained from the carbon, that is a activated carbon, is acting as an adsorbent with mixed micro and mesoporosity. Means the carbon activated carbon having both the structure, that is mixed micro and mesoporous structure. So what happens, wherein the amount of material adsorbed increases without the limit, means due to microstructure, microporous means some micropores are there, some mesopores are there, therefore the amount of material adsorbed increases. So micro means small, meso means medium. So due to this porosity, these different types of porosity, the adsorption type, the amount of adsorption is increases without the limit, and it is the natural adsorption approaches to unity, means it is a natural adsorption due to micro and mesoporosity, and it approaches to unity. So graph for the type third isotherm, that is the adsorption from the carbons with mixed micro and mesoporosity is adsorbed amount versus relative pressure, and the nature of graph is like that. So this is the nature of the graph for the type third isotherm. So in the type second, the adsorption, physical adsorption of gases by the non-porous solid, and in the type third, the adsorption from the carbons with mixed micro and mesoporosity. So next is a type 4 and type 5. So what happens in the type 4? So isotherms are convex towards the relative pressure axis. Means the nature of the graph for the adsorption isotherm type 4 and type 5 is the convex towards the relative pressure axis. Means the nature is convex towards relative pressure, that is relative pressure is plotted on the x-axis, and these isotherms are characteristics of weak gas solid interaction. Means why the nature of graph is like convex towards the relative pressure axis, because these isotherms are the characteristics of weak gas solid interaction. Means if there is very weak interaction between gas and solid, the isotherm is like that, it is convex towards the relative pressure axis. So type 4 isotherm describe multilayer adsorption process where complete filling of smallest capillaries has occurred. Means in the type 4 there is no, it is not limited to only monolayer, but here there is formation of multilayer, and it involves the complete filling of smallest capillaries. Means all the small pores can be filled by the adsorbent material, and this is called as a type 4. And the type 4 isotherms originate from non-porous and mesoporous solid. Means the type 4 isotherm is originating from non-porous structure, means the adsorbent having no pores and somewhat about the mesoporous solids. And the type 5, this type 5 isotherms originate from micro and mesoporous solid. Means this is the difference between type 4 and type 5. In the type 4 isotherms, these originate from the non-porous and mesoporous solid, but type 5 isotherms originate from the microporous and the mesoporous solid. And the example is the adsorption of water vapor on graphitized carbon black. Means this is an example of type 4 and type 5 isotherm. So what adsorption of water on the water vapor on the graphitized carbon black. So what is the nature of graph for the type 4? So if we plot a graph of adsorb amount versus relative pressure, so we got a graph like that. So here is the formation of multilayer, and very smallest capillaries are completely filled by the adsorbent. And the nature of the graph for the type 5 isotherm, that is a again plotted adsorb amount versus relative pressure. So we got a graph. So this graph is convex towards the relative pressure axis. Means we have seen that here relative pressure is drawn on the x-axis and the graph is convex. This graph is convex towards the relative pressure axis. So this was all about the type 4 and type 5 isotherm. So these are the 5 types of adsorption isotherm. The type first, type second, type third and type fourth and type 5. So these are the adsorption isotherms. Means the adsorption isotherms are the graph which are plotted against adsorbed amount against the relative pressure, and we got a different graphs for the type 1, 2, 3, 4 and 5. So the next point is the type 6. So what happens in the type 6? The isotherm in which sharpness of the steps depends upon the system and the temperature. Means the type of isotherm in which sharpness of steps, means how the nature of the graph is obtained, that depends on the system and the temperature, and it represents the stepwise multilayers adsorption on a uniform non-porous surface. Means this type 6 represent the stepwise multilayer adsorption on a uniform non-porous surface, and the step height now represent, means the graph has the some step height, and that step height represents the monolayer capacity for each adsorbed layer, and in the simplest case remains nearly constant for 2 or 3 adsorbed layers. Means the step height represents the monolayer capacity of each adsorbed layer, and it remains nearly constant for 2 or 3 adsorbed layers. Means if multilayer formation is there, then the step height remains the constant. And the example is adsorption of argon or krypton gas on graphitized carbon black. Means adsorption of argon gas or krypton on the graphitized carbon black at liquid nitrogen temperature. So this is the example of type 6 isotherm in which the sharpness of the step depends on the system and the temperature, and it represents the multilayer adsorption, stepwise multilayer adsorption on a non-porous surface. So what is how is the nature of the graph for this? So if we plot a graph of adsorbed amount versus relative pressure, so we got different steps. So here we got different steps. So what this step height, what is the step height of each step? That represents the monolayer capacity for each adsorbed layer. Means this step height represents the monolayer capacity of each that adsorbed layer. In the simplest case, it remains nearly constant for 2 or 3 adsorbed layers. Means this step height is nearly remains constant for 2 or 3 adsorbed layer, and the example of this type of adsorption isotherm is the adsorption of argon or krypton gas on graphitized carbon black. Means the adsorption of argon and krypton gas on graphitized carbon black but at liquid nitrogen temperature. So this was the last type of adsorption isotherm, that is a type 6 having adsorption on uniform non-porous surface. So the next point is the adsorption isobar. So what is adsorption isobar? What happens in the adsorption isotherm? Adsorption isotherm means temperature remains constant. So what happens in adsorption isobar? So iso means constant and bar means pressure. So in this adsorption isobar, pressure is a constant. So the effect of temperature on the rate of adsorption can be studied by the curves which are called as adsorption isobar. Means the effect of temperature on the rate of adsorption can be studied by the curves known as adsorption isobars, and the typical adsorption isobars for the physics option and chemist option are as shown in figure. So we have already studied that adsorption isobar is a graph drawn between extent of adsorption. In the earlier of the first point of the chapter we have already studied the Freundlich and Langmuir adsorption isotherm. So adsorption isobar is a graph between the extent of adsorption, that is x upon m, against the temperature, but this is at a constant pressure, because the adsorption isobar is a graph plotted against the temperature but at a constant pressure. So we know that adsorption is a exothermic process, because in the process of adsorption some amount of heat is evolved, therefore the adsorption is a exothermic process. And the adsorption isobar is a graph between x upon m, that is the extent of adsorption, versus temperature but at a constant pressure. So if we plot a graph of x upon m versus temperature T, so we got a nature of graph, and this graph is plotted against the constant pressure, because we are plotting the graph of adsorption isobar. So most important condition is the isobar, means pressure is the constant, and this is for the physical adsorption. So we have already studied that physical adsorption and chemical adsorption. So in the physics option, the graph is plotted the amount or extent of adsorption against the temperature, and here pressure is constant. So according to Le-Chatelier's principle, the adsorption should decreases with increase in temperature, means according to Le-Chatelier's principle, so adsorption and temperature are inversely related. So if the adsorption decreases, the temperature should decreases, temperature should increases, and this is true for the physics option, means only the physical adsorption, only in the cases in which the physical adsorption takes place, the Le-Chatelier's principle holds true, and the adsorption decreases with increase in temperature. But so here we see that adsorption is decreases as the temperature is increases. But in case of chemissorption, means in the case of chemissorption, that is in the case of chemical adsorption, what happens? The rate of adsorption first increases with rise in temperature, then reaches the maximum and again decreases. So because chemissorption requires a certain amount of energy called as activation energy. So if plot a graph of x upon m versus temperature, so we got a graph like that, and this is a graph for the chemical adsorption. So why this graph is different for the physical adsorption and chemical adsorption? In the physical adsorption, what happens? The x upon m, extent of adsorption versus temperature, decreases, but if we plot the graph for the chemical adsorption, the x upon m versus temperature, the first increases, reaches the maximum and then decreases, because in the chemical adsorption requires certain amount of energy called as activation energy, because here the chemical bonds are the formed. So this was all about the adsorption isobars for the physical adsorption and the chemical adsorption. So thank you. In the next lecture, we will study the last part of our surface chemistry chapter, that is the applications part. So the applications we will study in the next lecture. Thank you.